Now, President Biden has introduced the first image to be shown publicly from the James Webb Telescope.
The James Webb Space Telescope has redefined the boundaries of astronomical discovery. Its state-of-the-art capabilities have not only deepened our understanding of distant galaxies, but have also revolutionized our knowledge of the solar system's most enigmatic body, Pluto. With its advanced infrared sensors, the JWST has revealed new, startling details about Pluto's geological activity and its dynamic interactions with its moon, Charon, challenging long-held assumptions and opening new avenues of exploration. The revelations are shocking, so much so that esteemed physicist Michio Kaku has exclaimed that the James Webb Telescope has finally found what NASA was hiding on Pluto all along. So, what's the big revelation? Well, let's find out. Pluto. A planet no more. Once hailed as the 9th planet in our solar system, Pluto has undergone one of the most debated transformations in the history of astronomy. Discovered by Clyde Tombaugh in 1930, Pluto was initially celebrated as the outermost planet, despite its small size and eccentric orbit. For decades, it held the distinction of being the smallest planet in the solar system. However, by 2006, a shift in our understanding of celestial bodies led to Pluto's reclassification as a dwarf planet by the International Astronomical Union. This decision was based on the criteria that Pluto failed to clear its orbit of other debris, a key requirement for full planetary status. Instead, it joined a growing category of objects in the Kuiper Belt, an expansive region beyond Neptune, populated by icy bodies and dwarf planets. But that's not the most interesting thing about the wannabe planet. There's a lot more to this celestial body than what we see on the surface. Hang tight, as these revelations are truly mind-blowing. Before this reclassification, Pluto had already been the subject of intense study, primarily through NASA's New Horizons mission, which provided humanity's first close-up images of the distant world in 2015. The spacecraft revealed Pluto to be far more complex and geologically active than previously thought, showcasing vast plains of nitrogen ice, towering mountains of water ice, and even evidence of a subsurface ocean. These findings, coupled with the data from Earth-based telescopes, such as the Keck Observatory in Hawaii, provided crucial information about Pluto's atmosphere, surface features, and even the possible presence of organic molecules, suggesting that this distant world might be more like a planet than the icy, barren rock many had once imagined. Recently, the James Webb Space Telescope has added another chapter to this saga: what we know about Pluto. Long regarded as a frozen, desolate world at the outer reaches of our solar system, Pluto has increasingly defied previous assumptions about its nature. For much of the 20th and early 21st centuries, Pluto was considered a cold, inhospitable object, with temperatures plunging to as low as -375 degrees Fahrenheit or -225 degrees Celsius. Its surface perpetually coated with frozen nitrogen, methane, and carbon monoxide. The assumption was that beneath its icy shell, Pluto was nothing more than a lifeless frozen core, incapable of harboring any active processes. However, the groundbreaking data from NASA's New Horizons mission, followed by the unparalleled observations of the James Webb Space Telescope, have challenged this image. Pluto might harbor a subsurface ocean beneath its icy crust. The concept of a liquid ocean hidden beneath Pluto's surface seemed far-fetched at first, given the extreme cold and distance from the Sun. However, infrared scans of Pluto's surface and atmosphere have uncovered localized pockets of heat, suggesting that the dwarf planet might have pockets of liquid water beneath its icy surface. This environment could even offer the conditions necessary for life. The existence of a subsurface ocean could also explain some of Pluto's geological features, such as the large, smooth plains observed by New Horizons, as well as the surprising presence of complex organic molecules. This discovery has major implications for our understanding of life in extreme environments. Like Europa and Enceladus, moons of Jupiter and Saturn, Pluto could harbor the potential for microbial life. Moreover, Pluto has also revealed itself to be an active world. The New Horizons mission discovered cryovolcanism, or volcanic eruptions, driven not by molten rock, but by water, ammonia, and methane on the planet. These ice volcanoes on Pluto's surface are unlike anything seen on Earth. This has forced scientists to rethink the dynamics of the planet's interior, suggesting that, rather than being a cold, dead world, Pluto might be experiencing tectonic movements and active surface reshaping. New Horizons also identified surface features that appeared to be the result of tectonic processes, including faults and ridges that indicate the crust is stretching and shifting. These signs of tectonic movement suggest that Pluto's icy outer shell may not be as rigid and static as once believed. Instead, it appears that Pluto's surface is changing, with the crust slowly being reshaped by internal forces. This is supported by the detection of mountainous terrains and regions where the surface has been pushed upward or displaced by underlying forces. Due to its highly elliptical orbit, Pluto experiences extreme fluctuations in its distance from the Sun, which in turn affects the dynamics of its thin atmosphere. During its perihelion, when it is closest to the Sun, Pluto's atmosphere is at its thickest, composed mainly of nitrogen with traces of methane and carbon monoxide. As Pluto moves farther away from the Sun, its atmosphere begins to freeze and collapse, returning much of its volatile compounds to the surface as frost. This cyclic process, observed by both the New Horizons mission and the James Webb Space Telescope, reveals the dynamic nature of Pluto's atmosphere. Webb's infrared capabilities have provided further insights into how Pluto's atmosphere expands and contracts in response to seasonal changes. The gas clouds that form over the dwarf planet's surface during its warmer periods are not only intriguing in their own right, but they also provide evidence that Pluto's atmosphere is far more active and variable than previously believed. Perhaps the most exciting aspect of Pluto's atmosphere is the discovery of organic gases, which suggest that the dwarf planet might possess a far richer chemical environment than anyone expected. Observations made by Webb and the New Horizons spacecraft revealed a range of hydrocarbons and other organic compounds in Pluto's thin air. These molecules, including ethane and diacetylene, are complex carbon-based chemicals that are often associated with biological or chemical processes in other worlds. While it is still far from certain whether these compounds are the result of biological activity, their presence is noteworthy because they could potentially serve as building blocks for life. In Earth's own history, similar molecules have been crucial in the formation of life's basic structures. Pluto's surface is also far from uniform. From vast plains of nitrogen ice to towering water ice mountains, the ice planet has it all. One of the most fascinating features of Pluto's surface is the mysterious reddish coloring observed in certain regions, particularly around the equator and along the boundaries of large ice plains. These red deposits are believed to be tholins, which are complex organic molecules that form through the interaction of solar radiation with simple compounds like methane and nitrogen. Tholins are considered some of the first building blocks of life, and their presence on Pluto's surface raises intriguing questions about the planet's chemical processes. The tholins observed on Pluto are thought to be the result of ultraviolet light from the Sun interacting with methane in the atmosphere, breaking down the methane molecules into simpler components that then bond together into more complex molecules. These compounds could be similar to the ones that contributed to the formation of prebiotic chemistry on early Earth, offering clues about the potential for life in harsh environments and how organic molecules might have formed on primitive Earth. That's not all, far from it actually. Let's move a bit back and take a look at Pluto's neighborhood. Charon, Pluto's moon and geological activity. Pluto's largest moon, Charon has long been regarded as a frozen, inactive world, its surface covered in craters and deep canyons. However, recent findings from the James Webb Space Telescope have forced scientists to reconsider this notion and have revealed startling new evidence of geological activity on the moon. Scientists have discovered large, deep fractures along Charon's surface, which have been interpreted as signs of tectonic activity. These faults and ridges suggest that the moon's icy crust has been stretched and pulled apart by internal forces, likely the result of a subsurface ocean or a layer of slushy, partially liquid ice beneath the surface. This tectonic activity on Charon mirrors the types of geological processes seen on Earth, where tectonic plates move and shift over time. But in this case, it's happening on an icy body far from the Sun. The stretching of the crust in certain regions of Charon, such as the smooth, relatively young plains near its equator, hints that the Moon has experienced significant internal heating in the past, possibly driven by tidal forces between Pluto and Charon. These forces may have been strong enough to keep Charon's interior warm. Moreover, large, deep canyons, such as the vast Vastitas Borealis region, appear to be the result of the stretching and cracking of Charon's icy crust, which could only occur if the Moon's interior remained warm enough to maintain a liquid or semi-liquid layer beneath the surface. These features are similar to those found on moons like Europa, one of Jupiter's moons, where a subsurface ocean is believed to exist beneath its icy shell. Charon's geological activity has profound implications for the study of Pluto itself. Understanding the processes that shape Charon's surface and interior could provide clues about the history of Pluto's own surface and its potential for subsurface activity. Just as Charon's tectonic features are linked to its interior heating, Pluto's own surface features, including signs of cryovolcanism and tectonic activity, may be connected to similar internal processes. Pluto's orbital system is a remarkable example of a chaotic orbit, where its gravitational interactions with its moons, especially Charon, result in highly complex and unpredictable motions. Unlike the regular satellite-orbit relationship found in most planetary systems, Pluto and Charon are locked in a unique tidal interaction. This interaction means that they both always show the same face to each other as they orbit one another, a phenomenon known as mutual tidal locking. Their mutual orbit is highly elliptical, with the two bodies' distances from each other fluctuating dramatically as they circle their common center of mass. Over time, the gravitational forces between Pluto and Charon have become so finely tuned that any slight deviation from their orbital equilibrium could cause the system to destabilize. This sensitivity, coupled with the influence of other distant objects in the Kuiper belt and the Sun's gravity, creates an environment where small changes can have significant consequences, driving chaotic orbital variations over long periods. For example, the gravitational influence of other Kuiper belt objects, such as Eris or Haumea, can subtly alter the orbital paths of Pluto and its moons, resulting in long-term variations in their orbital parameters. Pluto is also accompanied by 4 smaller moons: Styx, Nix, Kerberos, and Hydra. These moons also interact with one another, creating additional complexities in the system's overall orbital mechanics. For example, Styx and Nix are in a gravitational resonance with each other, meaning their orbital periods are linked in such a way that their relative positions repeat after a certain number of orbits. These moons are believed to have formed from debris resulting from an ancient collision or capture event, which is further evidence of the chaotic and dynamic environment in which Pluto and its moons have evolved. Moreover, the fact that Pluto's orbit is somewhat eccentric and tilted relative to the plane of the solar system's other planets suggests that it might not have always been in its current position in the Kuiper belt. Pluto may have originated further inward, possibly in the region of the giant planets, before being gravitationally scattered outward by interactions with the massive planets, especially Jupiter. This potential migration of Pluto and other Kuiper belt objects may have played a significant role in shaping the current architecture of the outer solar system, influencing the distribution and characteristics of the trans-Neptunian objects we observe today. Additionally, the chaotic nature of the orbits of Pluto's moons can provide clues about the early conditions of the solar system. The interactions between these moons and Pluto may reflect the kinds of processes that shape the formation and evolution of planetary systems across the cosmos. Scientists have also used advanced computer models to simulate Pluto's future orbital behaviors. These simulations show that over millions of years, Pluto's orbit could undergo dramatic shifts, potentially altering its relationship with the Sun and other bodies in the solar system. This could have significant consequences for the dynamics of the outer solar system, including the gravitational interactions between other distant objects and the possible impacts on the Oort cloud, a vast region of icy bodies far beyond Pluto. Now, back to the ice world. Pluto's geological activity. Recent high-resolution images from NASA's New Horizons mission and data gathered by the James Webb Space Telescope have unveiled intriguing surface features on Pluto. suggesting that the dwarf planet has experienced resurfacing in the relatively recent past. One of the most striking features is the vast smooth plains of Sputnik Planitia, an expansive nitrogen ice field in Pluto's heart-shaped Tombor Regio. The smoothness and lack of impact craters in this region suggest that the surface is geologically young, likely resurfaced by some form of internal activity. Scientists believe that this resurfacing could be the result of cryovolcanism, where icy volcanoes erupt volatile substances like water, ammonia, and methane instead of molten rock. Such cryovolcanic activity, driven by internal heating, could be responsible for replenishing the surface with fresh ice and altering its appearance over time. Large-scale tectonic features such as faults and fractures in Pluto's icy crust further support the idea of an active geology, likely driven by the dwarf planet's interior heat. These tectonic movements may have been induced by the slow but steady internal heating, possibly from tidal forces exerted by Pluto's gravitational interactions with Charon. The similarities between Pluto and Charon's geologically active surfaces are significant, as they indicate that both bodies may share a dynamic, evolving history, rather than simply serving as ancient frozen relics from the early solar system. Both bodies exhibit features that suggest ongoing geological processes driven by internal heat and tidal forces, as opposed to being passive, unchanging objects left behind in the distant reaches of the solar system. The resurfacing on Pluto, combined with the tectonic and cryovolcanic activity on both Pluto and Charon, paints a picture of two dynamic planetary bodies that have experienced and may continue to experience internal and external forces shaping their evolution. The possibility of active geology also raises important questions about the potential for these bodies to support life, or at least complex prebiotic chemistry. On Earth, geological activity is often linked to the cycling of materials between the surface and the interior, a crucial process for the development of life. If Pluto and Charon are indeed geologically active, then it's possible that they have, or once had, environments where chemical reactions essential for life could take place. The discovery of internal heating and resurfacing processes on these bodies suggests that they may have been far more hospitable in the past than previously thought. Moreover, Pluto's gravitational pull on Charon could have caused tidal heating, which may have been a significant source of energy for geological activity on both bodies. The study of Pluto can also offer us clues about the past. Significance to solar system's genesis. Positioned beyond Neptune and between the scattered disk and the classical Kuiper belt region, Pluto is a pristine relic of the early solar system, often referred to as a fossil body. This positioning makes it an invaluable target for scientists studying the early dynamics of the solar system, as it has likely remained relatively unchanged for billions of years. Pluto's surface and atmosphere, which have undergone surprising changes and exhibited complex characteristics, offer profound insights into the mechanisms behind planetary formation and movement. The ice world's early evolution was shaped by processes not entirely unlike those that formed other planetary bodies in the inner solar system, albeit at much lower temperatures and in the absence of significant solar radiation. Understanding how volatile ices and organic materials on Pluto's surface interact and evolve under extreme cold helps scientists refine models of planetary formation in the outer solar system, particularly the behavior of objects beyond the snowline, where volatile compounds like water, methane, and ammonia freeze and remain locked in place for much of the solar system's history. The James Webb Space Telescope has also expanded our understanding of Pluto's environment. Using its advanced infrared capabilities, JWST has captured more detailed images and measurements of Pluto's surface and atmosphere than ever before. This includes better resolution of the distribution of methane and other organic gases in its atmosphere, revealing how these molecules interact with the sun's radiation and the dynamics of Pluto's seasonal changes. JWST's ability to observe infrared emissions from the dwarf planet allows scientists to track changes in Pluto's atmosphere that would have been difficult or impossible to observe with earlier space telescopes. Another critical aspect of Pluto's role in understanding the solar system's genesis lies in its relationship with its largest moon, Charon. The unique gravitational interaction between Pluto and Charon often described as a double planet system, offers a rare opportunity to study the forces that shape planetary systems and the evolution of moons in close orbits around their parent planets. Unlike other moons in the solar system, Charon is so large in relation to Pluto that the two bodies orbit a common center of mass, or barycenter, located outside of Pluto itself. This distinct feature has important implications for understanding tidal forces, orbital evolution, and the long-term dynamics of planetary moon systems. The gravitational interaction between Pluto and Charon may have had a significant impact on the composition of their atmospheres and surface features. By studying how Pluto's and Charon's orbits have evolved, scientists can gain deeper insights into the dynamics of moon-planet interactions, which are common throughout the solar system. Moreover, the Kuiper Belt, home to Pluto, is thought to be the remnants of the early solar system's building blocks, and its study can provide clues about the primordial conditions from which planets formed. Objects like Pluto that are left over from the early stages of planetary formation are sometimes referred to as planetesimals, which are the leftover chunks of material that did not form full-fledged planets, but played a crucial role in the formation of the solar system. By studying Pluto, scientists can learn more about the composition, movement, and behavior of these planetesimals, shedding light on the processes that influenced the formation of the gas giants, ice giants, and terrestrial planets. These early objects may hold the key to understanding the chemical and physical conditions necessary for the formation of planets and the development of life, especially when considering that some of Pluto's surface compounds are similar to those found on early Earth. Furthermore, Pluto can serve as a proxy for understanding other planetary systems that may be forming around distant stars. Studying Pluto's composition, its orbital mechanics, and its relationship with Charon could provide a model for understanding how distant exoplanets and their moons may evolve. So, is there any source of warmth in the ice world? After all, that is a vital ingredient for the rise of life, even a microbial one. Well, the problem is that Pluto is far away from the warming effect of our Sun. But wait, there's an unexpected twist here. Unexpected findings on Pluto's heat retention. For decades, Pluto was assumed to be a cold, inert body with no significant sources of internal heat. Given its small size, distant orbit, and the extreme cold of the Kuiper Belt, scientists believed that any remaining internal heat would have long since dissipated. However, recently, scientists have discovered that Pluto's internal processes are far more complex and dynamic than previously thought. The first clue is the subsurface ocean beneath its icy shell. This ocean, which remains in a liquid state despite the frigid surface temperatures that hover around -225 degrees Celsius, suggests that there is a significant, ongoing source of heat within Pluto. But how is that possible when Pluto gets no heat from the Sun? Well, one key factor is the tidal heating produced by gravitational interactions between Pluto and Charon. This interaction creates tidal forces that generate internal friction and heat within both Pluto and Charon. As Pluto and Charon orbit one another, they exert gravitational pull on each other, causing subtle flexing and deformation of their bodies. The result is the release of heat, known as tidal heating, which could account for the liquid subsurface ocean observed beneath Pluto's icy shell. These tidal forces are particularly effective at generating heat in small bodies that experience significant orbital eccentricities, like Pluto and Charon, where the Moon's gravitational forces cause constant variations in each body's shape and rotation. This heat could be the key to maintaining the internal temperature required for liquid water. Tidal heating is not a new concept in planetary science. However, the fact that it could be responsible for Pluto's heat retention has profound implications for our understanding of distant icy bodies. In the case of Pluto, tidal heating from Charon may not only be the reason for the subsurface ocean, but it could also explain the ongoing geological activity observed on its surface. For example, the cryovolcanic activity on Pluto's surface, which involves the eruption of icy material instead of molten rock, is likely driven by the heat generated by these tidal interactions. These eruptions, which have been observed in regions like the Sputnik Planitia, indicate that Pluto is not the frozen, inactive world that scientists once thought it to be. Instead, it is a dynamic planet with internal processes that challenge the notion of small, icy bodies as simple, dead remnants of the early solar system. In addition to tidal heating, Pluto may also have developed other backup systems for heat retention. For example, Pluto's icy shell may act as an insulating layer, preventing heat from escaping too quickly into space. This could allow for a more prolonged retention of heat within the planet's interior. Such insulating layers are common in other icy moons and dwarf planets. This discovery also has implications for future studies of other distant icy bodies in the outer solar system and beyond. For instance, moons like Europa, Enceladus, and Titan, which also possess subsurface oceans and are considered prime targets for the search for life, could be influenced by similar tidal heating processes. Understanding how tidal forces generate internal heat and affect the geology of bodies like Pluto and its moons could inform how scientists search for signs of life or ongoing geological activity in these distant worlds. Michio Kaku's take on NASA and Pluto. Renowned theoretical physicist and futurist, Michio Kaku has criticized NASA's traditional approach to exploration, particularly with regard to missions like New Horizons, which was launched in 2006 to study Pluto. While Kaku has praised NASA's technological capabilities, he has argued that the agency's mission planning can sometimes be too conservative and slow. The New Horizons mission, for example, took over a decade to reach Pluto, and could have been faster with more resources or alternative strategies, Kaku believes. He has suggested that NASA should look beyond the current pace of exploration and consider more ambitious projects that could quickly expand our reach into the outer solar system and even beyond. Regarding NASA's general approach to space exploration, Kaku has often voiced concerns about what he perceives as a lack of long-term vision. He has been a vocal advocate for a more expansive view of space exploration, one that extends to colonizing other planets and moons and harnessing space resources. He has urged NASA and other space agencies to focus on projects that lead to breakthroughs in space travel, such as developing faster propulsion systems or building sustainable bases on other celestial bodies. For Kaku, the discovery of dynamic features like Pluto's cryovolcanism or Charon's geological activity underscores how much more there is to explore in the solar system. In terms of Pluto specifically, Kaku has pointed out that the latest discoveries offer a wealth of new scientific opportunities. For instance, in his 2021 book, The Future of Humanity, Kaku mentioned that the idea of subsurface oceans and the possibility of life on distant icy bodies, like Pluto, was a groundbreaking revelation. This concept challenges traditional views of the solar system and expands our understanding of where life could exist beyond Earth. But that's not all. In his 2016 TED Talk, Kaku reflected on Pluto's surprising geological features, particularly the evidence of active cryovolcanism, which was revealed by the New Horizons mission. He expressed fascination with the planet's ability to harbor geological activity despite its distant, cold position in the solar system. Kaku referred to these findings as evidence that the solar system is far more dynamic than previously understood. A year later, Kaku sat opposite Joe Rogan for an episode of The Joe Rogan Experience and commented that Pluto's geological features, including mountains made of water ice and the presence of cryovolcanoes, could inform how scientists approach the study of other icy moons in the outer solar system. This helped propel his argument that other moons and dwarf planets could harbor life or exhibit similar dynamic features, expanding the scope of planetary science. In an April 2017 interview on PBS NewsHour's Great Minds segment, Kaku stated that humanity must focus on long-term projects in space exploration. He argued that these missions should not just be about scientific curiosity, but should also aim to build sustainable human colonies and expand the reach of human civilization beyond Earth. So, what does all of this mean? Well, the future will indeed be radically different for space exploration. Implications for space exploration and astrobiology. As a frozen world located far beyond the Sun's habitable zone, Pluto's ability to sustain liquid water beneath its icy crust is a profound discovery that reshapes our views on life in extreme environments. This finding may open new possibilities for life on other frozen worlds located beyond the conventional habitable zone of a star. Pluto's newfound potential for harboring life pushes scientists to reconsider the search for extraterrestrial life on similar moons and dwarf planets in the outer solar system. Moons like Europa, Enceladus, and Triton, which are also known to have subsurface oceans beneath their icy surfaces, may offer more hospitable environments for life than previously imagined. The ongoing search for life in our solar system has traditionally focused on Earth-like planets in the Goldilocks zone. This changes now. Pluto's dynamic characteristics suggest that even in the coldest, most remote parts of the solar system, life might exist under conditions we never considered viable. These findings may prompt a re-evaluation of the types of environments that could support life, expanding the scope of astrobiological research to include icy moons and dwarf planets that were once thought to be dead, inhospitable worlds. Moreover, the James Webb Space Telescope has detected organic compounds in Pluto's atmosphere. The presence of these complex molecules, which are the building blocks of life as we know it, could serve as a model for identifying similar substances on distant exoplanets. These compounds may indicate that Pluto has the potential for life in a way previously thought impossible, but they could also offer a framework for identifying habitable conditions elsewhere in the universe. If organic compounds are found on other exoplanets or moons, they would be a key indicator of the possibility of life. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.